Okay, so we're going to be talking about rational functions and polynomials in this video. So let's say we have this function y equals 2x. As you can see, the x has no exponential value. Therefore, the degree of it is just 1. Now let's say we have another one, y equals 5x to the power of 0. That exponential value will give you the degree of the whole polynomial, and it is degree 0, as you can see. Next one, let's say we have y equals 3 plus 2x cubed. Now, as you can see, this polynomial has x variable with exponential value of 3, therefore making the degree of it 3. So now let's talk about why the degree of a polynomial is important to us. So let's say if a polynomial has odd degree, the polynomial's graph will look something like this. So yeah, odd degree polynomial. This is what the graph looks like. The end behavior, as you can see, is from top right to bottom left. And this is known as end behavior. So now, let's say we have an even degree polynomial. And for those that, just in case for some reason you do not know what an even degree is, that's 2, 4, 6, 8, 10, and so on. So, and the graph for an even degree polynomial will have an end behavior that looks something like this. Kind of like a quadratic function. Okay, so now we're gonna go over long division with normal numbers and then long division with polynomials. So let's say we are trying to divide 527 by 3. If you don't remember, here's how we set it up. We go through our long division, throw it back to elementary school, we carry it, we bring it down, we keep going. This is kind of a long process right now. As you can clearly tell, I have not done this in a long time. Alright, so now we are left with only 2. As you can tell, I'm labeling the different parts of our division statement right now. 527 as our quotient. And here's the division statement we can come up with. 527 is equal to 175 times by 3 plus by 2. And that is the formula for division statement. Okay, so now we're going to apply the same basics of long division to polynomials. Pretty much we're going to set up our division statement the same way. So let's say we're dividing x cubed plus x squared plus 2x minus 10 divided by x minus 5. So we just go through one by one. As you can tell, we will keep trying to get the least remainder as possible and see if we can get to preferably a 0, which is highly undoubtable right now. Feel free to pause the video if you need. to see how, and if you need, just like slow the pace down a little. It is the same concept as long division, but all we're doing now is multiplying x values together and subtracting and adding x values. But the basis is still the same. Now we can come up with our division statement. X cubed plus x squared plus 7x minus 10 is equal to x squared plus 6s plus 37 times x minus 5, and a remainder, which was 175.
Again, x cubed minus 2x squared plus 3x minus 4. We're going to divide that by x minus 2. What you do in this case is, whatever we're dividing by, so notice there's a minus 2, it's x minus 2. We actually take the opposite sign, and we'll use positive 2, and that's what you stick outside. And then notice I have 1x cubed minus 2x squared plus 3x minus 4. Notice there's no terms missing. It starts at the third degree, second degree, first degree, and then we just have a number. All we do is we write the coefficients. So 1, there's a negative 2 in front of the x squared. There's a positive 3 in front of the x. And there's a negative 4 just hanging out. And with synthetic division, what you do is, the first term, you just drop it right down. There's nothing to do. And then the idea is we multiply. So I'm going to take positive 2 times 1, and then stick that number in the next spot. So it says positive 2 times 1 will give us positive 2. And then what we do is we add those numbers together in this column. So negative 2 plus 2 is going to give me 0. And then we repeat this process. Now we take positive 2, multiply it by 0, and that's what we stick in the next column. So it says positive 2 times 0 is just going to give us 0. So if we add those together, we'll get positive 3. And then again, I take positive 2 times positive 3. Let me erase my little red dots here. We'll take positive 2 times positive 3. That'll give me positive 6. We add the columns together, and we get the number 2. This last number is going to be your remainder. Remainder. See if I can spell correctly here. And what it says is, in summary, it says we can actually, so the numbers on the bottom are what are important. Okay, so it says we can actually rewrite x cubed minus 2x squared plus 3x minus 4 divided by x minus 2, so I'm going to keep my numbers at the bottom. It says we can actually write that as, okay, so the highest power was x cubed. Make things 1 degree less. So this is going to go with my x squared term, this is going to go with my x term, this is going to be my constant, and again, the other part's my remainder. It says we can actually write x cubed minus 2x squared plus 3x minus 4 divided by x minus 2 as 1x squared plus 0x. So usually 0x, we'll just leave that out, so I'm going to erase it. So 1x squared plus 3, and then my remainder is 2, and we put that over whatever we were originally dividing by, which is x minus 2. And now we have broken up our original fraction into something a little bit more simple, okay? So this would be your solution after you did the synthetic division.
So the remainder theorem, pretty much how it works is, let's say we have x squared plus 5x plus 6, and we're dividing it by x minus 3. After we go through our division and we find everything we need, we realize that 30 is our remainder. If we were to plug in 3 into the function, 3, which is the opposite of minus 3, which is right here. So if we were to plug in 3 into the function p of x, we would get a remainder of 30, which is equal to what the remainder of what we got when we used our division to find. Now, so with that, we can tell that after we already went over this equation, dividend equals quotient times divisor plus remainder, we can tell that in polynomial terms, p of x is equal to x minus a times q of x plus r. By putting x as a, we can simplify the p function into p of a equals the remainder, which means whenever we have a situation like this, let's say if we were to change this to x squared plus 5 divided by x minus 1. If we were to plug in 1 instead of into the function, we would get the remainder and not have to go through the long division. The next thing we're going to talk about is the factor theorem, and this is another step in the direction that we will need in order to figure out how to solve any sort of polynomial in any degree. So the factor theorem is, let's say we have a number a and a number b. If we were to multiply them together, let's say it would equal number c. The factor theorem, the basics of it is that it says when we multiply two numbers to equal another number, the factors of number c will equal a and b. In other words, if we were to multiply a and b together, it would equal c. So pretty much with using that, we would also translate that into polynomials, which we have done in previous years also. So let's give another example. Let's say we multiply 2 times 3, it would equal 6. Factors of 6 are 2 and 3. It's one of the factors that we could have. Now this can be further applied to polynomials. Let's say we have an x squared minus x minus 6. We've done this in the previous years, but let's say we were to find the factors of this. The factors of this would be x minus 3 times x plus 2. In other words, if let's say this is A, let's say this is B, and let's say this is C. If we were to multiply A by B, we would get C. Now, where it gets interesting is, if we were to divide C by A, we would get B. And that is proven if we were to use our long division. And it's the other way around also. If we were to divide C by B, we would get A. And that's pretty much the basis of factor theorem. Additionally, in order for one of these to be a factor, if we were to divide C by A, as you can tell, we would not be left with any remainders. We would just be left with B. Now, that helps us in situations in which we could possibly estimate or guess and find a function's factors by just testing out the a value into the p of x function, as we talked about earlier, to find out if the remainder will be 0 or not. If the remainder is 0, we will end up knowing that that is one of the factors. So let's say, for example, we have a function x cubed minus 6x squared plus 3x plus 10. And we were trying to find one of the factors in order to be able to find the others. And let's say the question gives us a couple choices of which of these could be our factors, and we would have to find out which one is the factors. So, for example, pretty much how it works is you would start with numbers, small numbers like 1 and 2, and you would work your way up and down the negatives and the positives to find out one of the factors and go from there in order to be able to factor your function. So let's say we were trying to test out if x minus 2 is a factor of this. All you would have to do is plug in the a value here, which is 2, into the function and see what the remainder would be. So 2 cubed minus 6 2 squared plus 3 2 plus 10. Now, if you were to punch that into your calculator, you would see that the value would be 0. Therefore, x minus 2 is a factor. So, here's an example of how we can factor a polynomial. So, right now, as you can see, our constant at the end of our p of x function is 24. So first thing we're going to do is write out all the possible factors of 24. As you can see, I've already done that. The list goes pretty long, and my suggestion is that we start with the smaller numbers and use the remainder theorem to check for any factors. So when we start with p of 1, we are actually checking for x minus 1 being a factor. As you can see, neither 1 or negative 1 give a remainder of 0. Therefore, neither x minus 1 or x plus 1 is a factor. Now, moving on to the next factor that we're going to try is p of 2, which is actually testing x minus 2. As you can see, as we plug in the value of 2 to the function, we do get a remainder of 0. Therefore, x minus 2 is a factor. So now when we go through our synthetic division, which was explained earlier by the YouTube video I found, which explained it way better than I ever could, we go through and divide x minus 2 to get another factor. Then we would move to the next possible factor and see if that gives us a remainder of 0, which luckily it does. And now we are left with another remainder of 0 and another factor of another x minus 2 factor, which now leaves us with the factors x minus 2, x plus 2, x minus 3, and x minus 2. Now, as you can see, our x minus 2 has a even multiplicity, which will help us later on in how we're able to graph it. Okay, so now we will be talking about the 3 different types of rational functions, which will bring us to the end of the content we will go over in this video and get us to making our connections to the outside world of these chapters. Okay, so the first type of rational function you could run into throughout pre-calculus 12 is called the bottom-heavy rational function. And pretty much that's pretty self-explanatory. What it means is that, let's say this is our function right here. The function, if the denominator has a higher degree than the numerator, it makes it a bottom-heavy function. And now, what does that mean? In a bottom-heavy rational function, the function asymptote is always at the x-axis. So here's a rough sketch of the graph we were just talking about, the function we were just talking about. Now, a couple key points about this function. As you can see on the bottom, if we were to factor x squared plus 2x minus 8, it would be x plus 4 times x minus 2. Now, at every point on the denominator where one of the factors will equal 0, there will be a vertical asymptote. And a vertical asymptote is where the graph will never cross that line, and I will show the graph in a bit, but yeah. So on the bottom right now on the denominator, we have x plus 4 and x minus 2, which means if x was to be 4, one of the denominators would be 0, and 0 times x minus 2 would be 0, and x minus 2 divided by 0 would give you a value that does not exist. And on the other hand, if x was to be 2, we would also get a denominator of 0, which would give us another asymptote at which we cannot have x minus 2 be divided by 0. Now, as you can see on right now, the asymptotes we have, they're not at the same point, which means that they have odd multiplicity. Let's say it was x minus 2 times x minus 2, there would be 2 factors of the same, which means it would be even multiplicity. Now, what does that mean? If the multiplicity of the asymptote is odd, the graph will be asymptotic in the opposite direction. If the multiplicity of the asymptote is even, the graph will be asymptotic in the same direction. So right now, because at x minus 4 and at x minus 2 it's odd multiplicity, you can see that at x equals to 2, the graph is going up and down different directions, and the same on the other side. Another key point we need in order to draw a graph of this function is the function asymptote. And as we went over it, because it is bottom heavy, the function asymptote will be at y equals to 0. So right here, we have our vertical asymptotes and a horizontal one right here. Now, in order for us to be able to know the x-intercepts, which only we have one right here, as you can see, we would have to go back to our function right here and pretty much we would have to set the function to 0 in order for us to be able to calculate the x-intercept, because at y equals to 0, we will have an x-intercept. So right here, 0 equals x minus 3 divided by x plus 4 times x minus 2. So now we know that if we had 3 as x right here, we would have 0 on the top, which would make everything here equal 0, which would give us an x-intercept at 3 right here. And pretty much that's the steps you need in order to be able to graph a bottom-heavy rational function. Now, for the last type of rational function, which is our third type of function, is a top-heavy rational function. Top-heavy polynomial functions may have asymptotes that are either vertical, slanted, or even curved like a polynomial. To find the asymptote, we have to perform polynomial long division, write the division statement in the form of p of x equals q of x plus r over d of x. The asymptote will have the equation q of x. So what that's telling us is that we have to go through with long division, find our q of x, which is our quotient, and our remainder, and we would have to look at that equation and spot the q of x, and that would be our function asymptote. Alright, so let's say in this example, we have f of x equals x squared plus 2x and x minus 2. As you can see, we can already find our vertical asymptote, because right here, if x was equal to 2, we would have 0 on the bottom, which would give us a value that does not exist. So already we have our vertical asymptote at hand. Now, to find our function asymptote, as mentioned above, we would have to go through synthetic division and find our p of x equation. And here it is right here. X squared plus 2x equals x plus 4 times x minus 2 plus 8. Now, as mentioned above, we would have to isolate q of x in order to find the equation of our function asymptote. And right now, our q of x is here. So we have to use algebra to find our q of x. And the way in which we do that is right now, we can't have this whole thing be our q of x. We need one straight line, or one line, if I should say, as our function asymptote. So we have to divide both sides by x minus 2, which we have, which would give us 8 over x minus 2 and x plus 4 and x squared plus 2x over x minus 2. Now that is our function asymptote. So let's move on over here and let's see all the information we have. So now we know that the vertical asymptote is at x equals to 2. Function asymptote at y equals x plus 4. X-intercepts at, if we were to go through it, make the function equal 0, we would see that we have an x-intercept at 0 and 2. And how we got that was we set everything to 0, got rid of the new denominator because that just goes away when you multiply both sides by the bottom, and we would factor that out, and we would see that if we had x times x plus 2, it would equal x squared plus 2. Therefore, our x would have to be 0, or our x would have to be negative 2 in order for all of that to equal 0. So now we have x-intercepts at 0, and at x equals to 0 and x equals to negative 2. Now for our y-intercept, we would have to allow x to be 0, plug everything instead of x at 0, go through, plug it in, we see we have y-intercept at 0, so that's perfect. And now, here's the breakdown. We have x-intercept right here, y-intercept right here, we have a vertical asymptote right here, and we have our function asymptote right here. And because we know that we have odd multiplicity as we found before right here, multiplicity is odd because we only have one asymptote on the bottom, so there's no way we could have even multiplicity. That is why we get at the vertical asymptote, we get one going all the way to the top and one going to the other side. And yep, that is pretty much the breakdown of different types of rational functions and how you have to be able to graph them. Now, one way to relate this chapter to the real world is how we use polynomials in our everyday lives. So in a polynomial function, there's variables and there's constants. The variables are being the y's and the x's, and the constants being the coefficients and the other parts of the polynomial function. Now, for example, let's say you make just a random number. Let's say you make, I don't know, like $3,000 a month. And out of that $3,000, $50 every month is paid for your phone plan. Let's say you spend $100 a month outside with your friends, grabbing food, stuff like that. Let's say you spend $30 on your gym membership. All these are variables that you are aware of in your daily life, and changing these variables will affect how your daily budget and your monthly budget is functioning. So let's say, for example, one month you decide to cut back on going out with your friends. Now that variable that used to be in your equation in your mind of how much money you would spend going out with your friends is now a smaller value, therefore leaving you with more money to spend on other things or more money to just have. Therefore, we subconsciously use polynomials every day to manage our money and our life, and not even just money. Let's say in a day you have 24 hours. Let's say you're awake for all the 24 hours. Let's say you spend 10 hours of it at school. Let's say you spend 2 hours working out. Let's say you spend 3 hours doing homework. All these are different variables of the equation of, like, let's say 1 day of your life. And by changing some of these aspects of your life, you are affecting every other aspect, and you're leaving room for changes in the other aspects of your life. That is how constants and variables in a polynomial equation can be related to your daily life. And yeah, that's one of the connections I made as we were going through this chapter. And it's just subconsciously that we use constants and variables in our daily lives. Additionally, we use polynomials even at an earlier age when we start to earn allowances and when we get our first job as teenagers. We sort of make an equation in our head of how much money we're going to make because we're excited to finally start saving our money. So let's say our parents decide to give us as young kids, let's say $5 a month as our allowance, and in our head we do a little bit of simple math and realize that in 2 months we will have $10. Now that's actually a polynomial function. Now we know that is equal to that we can restate that as y equals 5x. Well, y being the total amount of money we have, and x being the amount of months, and 5 being the coefficient. That equation states that every x, which is every month, we earn $5. So with 3 months, 5 times 3, we have $15. And that goes the same with our first job, actually. So let's say we are getting paid $10 an hour for our first job, and we can state that in also another polynomial equation. Let's say that as a student I am able to work 2 days a week, being on the weekends. Now I know that I can work 2 days, but I don't know how many hours I can work. So our variable would be an x. So now we have a $10 per hour times the 2 days that we are going to work, but we don't know how many hours. So now we have 10 per hour, which is per x. So 10 times x times 2 days, which is how many days we can work. And that is another polynomial function that we started working with as early as our first job, to find out how much money we would make in a weekend, and how much money we would make in a month, how much money in 2 months, how much money in a year. And that's another way that I realized that we've been exposed to polynomials since a young age.